Howdy. Let's start off with a quick look at this video, following the white rabbit. I know stuff I'm probably not supposed to know. Now let's just have a quick look at that, and then we will talk about an article. Or maybe just read it.
He tried to measure something here, and then it exploded. The same thing happened. Maybe it was this one. Or this one. I haven't seen them exploding, but he did. I just noticed that there was a different one. And then it turned out that he was putting the beam on that. I think here is visible better. That one exploded as he tried to measure, and this one exploded as he tried to measure. And this.
Alright, now you got the idea. You can watch the whole video when you're interested into. But now let's go over quickly to the article. For this we go over to SciTech Daily. The Dolomite Problem. Scientists resolve a 200-year-old geology mystery. Topics: computer science, material science, University of Michigan. January 6, 2024. Professor Wenhao Sun shoves off dolomite from his personal rock collection. Sun studies crystal growth of minerals from a material science perspective. By understanding how atoms come together to form natural minerals, he believes we can reveal fundamental mechanisms of crystal growth which can be used to make functional materials more quickly and efficiently. To create mountains from dolomite, a common mineral, it must periodically dissolve. This seemingly paradoxical concept could help make new defect-free semiconductors and more. For 2 centuries, scientists have failed to grow a common mineral in the laboratory under the conditions believed to have formed it naturally. Now, a team of researchers from the University of Michigan and Hokkaido University in Sapporo, Japan, have finally pulled it off, thanks to a new theory developed from atomic simulations. Their success resolves a long-standing geological mystery called the Dolomite Problem. Dolomite, a key mineral in the Dolomite Mountains in Italy, Niagara Falls, the White Cliffs of Dover, and Utah's Hodos, is very abundant in rocks, older than 100 million years, but nearly absent in younger formations. Wenhao Sun, Dow early career assistant professor of material science and engineering at the University of Michigan, and Yeon-so Kim, a doctoral student of material science and engineering in Professor Sun's research group, show off dolomite rocks from their lab's collection. The 2 scientists have developed a theory that could finally explain the 2-century-old puzzle surrounding dolomite's abundance in Earth. The importance of understanding dolomite growth. If we understand how dolomite grows in nature, we might learn new strategies to promote the crystal growth of modern technological materials, said Wenhao Sun, the Dow early career professor of materials and science and engineering at UAM, the corresponding author of the paper recently published in Science. The secret to finally growing dolomite in the lab was removing defects in the mineral structure as it grows. If minerals form in water, atoms usually deposit neatly onto the edge of the growing crystal surface. Now one might ask that, how does the water know where the surface is? Anyway, however, the growth edge of dolomite consists of alternating rows of calcium and magnesium. In water, calcium and magnesium will randomly attach to the growing dolomite crystal, often lodging into the wrong spot and creating defects that prevent additional layers of dolomite from forming. This disorder slows dolomite growth to a crawl, meaning it would take 10 million years to make just 1 layer of ordered dolomite. The structure of a dolomite crystal etch. Rows of magnesium, orange spheres alternate with rows of calcium blue spheres and are interspersed with carbonate black structures. The pink arrows show the directions of crystal growth. Calcium and magnesium often attach to the growth edge improperly, which stops the dolomite growth. All right. Luckily, these defects aren't locked in place because the disordered atoms are less stable than atoms in correct positions. They are the first to dissolve when the mineral is washed with water, repeatedly rinsing away these defects. For example, with rain or tidal cycles, allows a dolomite layer to form in only a matter of years. Over geologic time, mountains of dolomite can accumulate. Geologic time. Advanced simulation techniques. To simulate dolomite growth accurately, the researchers needed to calculate how strongly or loosely atoms will attach to an existing dolomite surface. The most accurate simulations require the energy of every single interaction between electrons and atoms in the growing crystal. Such exhaustive calculations usually require huge amounts of computing power, but software developed at UM's Predictive Structure Material Science Center offered a shortcut. Our software calculates the energy for some atomic arrangements, then extrapolates to predict the energy for other arrangements based on the symmetry of the crystal structure. Yeah, the circuitry, said Brian Pukala, one of the software's lead developers and associate research scientist in UM's Department of Material Science and Engineering. That shortcut made it feasible to simulate dolomite growth over geologic time scales. Dolomite is a mineral so common in ancient rocks that it forms mountains like this namesake mountain range in northern Italy. But dolomite is rare in younger rocks and could not be made in the lab under the conditions at which it formed naturally. A new theory helps scientists grow the mineral in the lab at ordinary temperature and pressure for the first time and could help explain the scarcity of dolomite in younger rocks. Now let's just get on with that. Each atomic step would normally take over 5,000 CPU hours on a supercomputer. Now we can do the same calculation in 2 milliseconds on a desktop, said Yeon-Soo Kim, a doctoral student of material science and engineering and the study's first author. Practical application of and testing of the theory. The few areas where dolomite forms today intermittently flood and later dry out, which aligns well with Sun and Kim's theory, but such evidence alone wasn't enough to be fully convincing. Enter Yuki Kimura, a professor of material science from Hokkaido University, and Tomoya Yamazaki, a postdoctoral researcher in Kimura's lab. They tested the new theory with a quirk of transmission electron microscopes. Electron microscopes usually use electron beams just to image samples, Kimura said. However, the beam can also split water, which makes acid. That can cause crystals to dissolve. Usually this is bad for imaging, but in this case, this solution is exactly what we wanted. After placing a tiny dolomite crystal in a solution of calcium and magnesium, Kimura and Yamazaki gently pulsed the electron beam 4,000 times over 2 hours, dissolving away the defects. After the pulses, dolomite was seen to grow approximately 100 nanometers, around 250,000 times smaller than an inch. Although this was only 300 layers of dolomite, never had more than 5 layers of dolomite been grown in the lab before. The lessons learned from the Dolomite problem can help engineers manufacture higher quality materials for semiconductors, solar panels, batteries, and other tech. In the past, crystal growers who wanted to make materials with out defects, we try to grow them really slowly, Sun said. Our theory shows that you can grow defect-free materials quickly if you periodically dissolve the defects away during growth. With a laser. With electricity. Electron. With an electron beam. Gently pulse the electron beam 4,000 times over 2 hours. The electron beam. Yeah, like happened in the video I showed you in the beginning. So electron microscopes, they are very interesting. Now they made dolomite in the electron microscope with an electron beam. And I've been writing about the influence of electricity in rock forming processes and stuff like that. So this paper is a very good one. That's just basically the article to the paper, which you can find here. Now let's check it out if it's a free one or not. Check access. Dolomite, the calcium magnesium carbonate, is one of the major minerals in carbonated rocks. However, growing the mineral under laboratory conditions has proven very difficult, resulting in the so-called Dolomite Problem. Kim et al. May have solved this problem by identifying the need to cycle the solution between the unsaturated and the supersaturated conditions. See the perspective by Garcia Ruiz. Cycling speeds up crystal growth 10 million times and may be imperative for making large amounts of dolomite. This observation is consistent with where we see dolomite formation in nature, in coastal and evaporative environments. So what about the electron beam? Anyway, you can read the stuff. I think I tried to get this paper somewhere if it's not available here. Check access. Let's click on that. Let's see, add in, become an AAA. Maybe I am, I don't know, maybe I have to try. Some of these things where you are required to get access by some account or something. You just make an account, it doesn't cost a thing. Just try. Yeah, but that's very interesting. And greetings to Michael Steinbacher. Dolomite was his best friend. Yeah. That's very interesting. But anyway, I think I leave it here. I don't expect anyone else being so excited about this than me. But anyway, now you have something to think about if you're bored. Hopefully you aren't. But anyway, thanks. Bye.